So with that, that leads us into how can you tell what kind of motion you have based on the foliations and lineations of this myelinite. In this example here, this drawing, the top rock block is moving to the right, the bottom is moving to the left, and it's distorting the myelinite between, this is the fault gouge that got buried so deep that it's a lot of pressure and heat. It turns into myelinite, and we have foliations, and on the surface we have lineations, and the orientations of them can tell us about the motion of the fault. Up on the surface we can tell the motion of the fault because of things that have been displaced. 15 kilometers below the surface of the Earth, there are no fence posts or roads or things of that nature to show us the displacement, so we look at the myelinites. The grains can get stretched and distorted. You can see here that both cases we have the top half is moving to the right, the bottom half is moving to the left, so we have shearing going on, and the grain is getting these tails. And it can form in two different ways. Sometimes the whole grain seems to be swooping off into the tail, sometimes just parts of it. And you can see here from this kind of step through how it can get these tails growing on it. Sometimes the tail is the mineral around the grain, and sometimes the tail is made up of the grain. This first type is called a sigma type grain tail. You can see here a pencil drawing and then an actual photograph of a sigma type grain tail. The tail is basically as wide as the grain and then tapers off on either side. On the other hand, a delta type, so we've got the little Greek symbol sigma and the Greek symbol delta. So this is a delta type grain tail. And you can see in this photograph the grain tails are nowhere near as wide as the grain. They are thin tails at all points along it. Although they do, of course, taper off and kind of disappear into the matrix. Now, the orientation of the tails tells us about the fault motion. Like if I back up here, clearly the top half was moving to the right, and the bottom half was moving to the left. So it gives us a sense of shear motion in this picture. However, depending on what orientation you are seeing a cut, it'll look like a left or a right or a sinistral or dextral fault motion. Unlike standing on the surface of the Earth looking at a transform fault where it doesn't matter which side of the fault you stand on, it's the same sense of motion. Now it's almost as if you could be standing with your feet at the ground surface, but your body is down into the ground, so you're like inside the Earth looking up at the surface, and now the sense of motion is reversed. Because if we have a road cut and the solid rock is on our left, like right here, we see a sinistral or a left lateral sense of motion. However, if the road cut is to our right and we're looking at it, we're seeing a dextral or right lateral. So it's kind of ambiguous to talk about right lateral and left lateral when you're down inside the Earth. That's useful at the Earth's surface, but down deep inside is kind of, it's all about which way you're looking at it. So it's based on observation direction. Sometimes it's ambiguous what you're even seeing because it's into or out of the surface that you're looking at. But in all of these three underground, or down in the Milonite images, we had the same thing going on, where this top of this Milonite was moving out of the page and the bottom of the Milonite was moving into the page. The rock can also fracture, not just get these tail elongations, but it can fracture, and it can fracture close to the direction of foliation, and it can fracture across it. So if we have a foliation and sense of motion that is similar to the orientation of the fractures, so less than 45 degrees. So basically, it's like you have a deck of cards sitting there on the table, and you slide the top of the deck so you've got some shearing going on, and the foliation is in the same direction as the motion, and the fractures, which is basically between each playing card, is a fracture because it's not solid. It's all in the same direction. So that's like in this top image here. On the other hand, if you take your deck of cards and you stand it on its edge, and then you shear it, you tilt it a little bit, the sense of motion will be the top is moving to one side relative to the bottom, but the fractures are near vertical, and the sense of motion along each fracture as the cards slide past each other is in a fairly vertical direction. So now we have a mismatch between the fault shear motion and the fractures and the foliations. And so this gives us it tells us about what kind of system we have going on when we look at this, and we call it synthetic fractures and antithetic fractures. So synthetic fractures, it's kind of like they're synthesizing and building on, everything's lined up, the fractures, the fault motion, the foliation, everything's all in the same direction. And then antithetic fractures is when the fractures in the sense of motion are at a different greater than 45 degree angle. Mica fish are not fish, they're not fossils, but little mica grains that get split off from a larger mica grain, and they get this oval shape to them. So like in this top here, this was probably a mica fish off of some larger mica grain, and the shearing continues because this is a fault zone, and another little mica fish splits off, and so now we have another little oval down here, and we have this piece that's missing the oval, and as the shearing continues, it will be kind of straightened out, and little tails forming as it gets stripped away, probably a sigma formation, and same with this, unless of course another microfish breaks off, and slowly the pieces get smaller and smaller as these little mica fish break off. We can also have rotated grains. Sometimes they rotate a lot. because the fault just continues to move over time. So you can see down here 2 photographs, fairly small scale grains, but rotated grains. Sometimes we can see this, a bit bigger, not needing a microscope to see, just hand sample size rotated grains. You can see that as we have the shearing going on, the grain between the 2 planes is going to rotate almost like a wheel.